analysis of 2D stresses. We have when I say analysis of 2D stresses is one plane, the stresses at any one of the plane of the structure or the member is given to you, and you need to analyze them. For example, you need to find whether that's the maximum stress or not, or there are other planes where the stresses can be maximum. What could be its shear stresses and all those details, right? So these are the three things that we need to analyze or find out from stresses across elements. And we have seen for for a 2D, not 2D member, for a biaxial stresses, for example, 2D planar stress, how to get this thing. So when you have a 2D planar stress, your stress elements are given by sigma x, tau xy at one of the plane. And since it is a 2D planar stress, we need to give the stresses along the perpendicular direction. Okay, another perpendicular plane. So this plane, y plane, is perpendicular to your x plane, right? So this is your xz plane, and that is your yz plane. So you need to give stresses along both the planes. This is customary. Right, now this is your sigma x, so that becomes your sigma y, and then you have a tau xy. This tau xy will remain same in magnitude all through, but the directions are keep on changing. Right? So what we write here is sigma xx, tau xy, sigma y. This is your stresses at a plane which is like this. So let us call this as a 0 degree plane. So this is the stress at a 0 degree plane. Now, suppose, we have to change the plane. The reasons we have discussed that the failure can start happening from any plane, right? So we need to change the plane, or there is a welding along that plane. For example, suppose you have plate, and you have welded the plate from here, right? So that side of the plate, something different, and this side is something different. You have this weld in between. And what you want to know is, to weld it, you need to know what are the stresses along this plane, right? So you will try to find the stress along that. So you will take a very small element here, and that element will be oriented, right? It's not straight. So this oriented element, the stresses will be along this direction, along that direction, and this here. So this is not same as having another element which is here, right? This is like this, and this one is like this. So you need to find the stress because of various reasons. One, the failure can start from that direction, or you need to find what are the maximum directions of maximum stress directions that can along. You need to find the directions along which maximum. For example, we found we took a bar member, right? When I say a bar member, it's an axial member, and there was a P force here. And we choose a small area here, and the stresses were along this direction, right? Here, and the sigma here. And we saw that the sigma along your axis, if you have this angle of orientation theta, it changes like this. Whereas shear stress, this is your sigma. Whereas the shear stress changed like that. Okay, this was my tau shear stress. So as you can see, the stress actually varies with the angle at any point. Okay, and it becomes important to know what are the maximum stresses and at what angles they act. That's why we do stress transformation. Okay, so given another plane, let's say this is another plane, and it makes an anti-clockwise angle of theta. We need to find the stresses along that, the planes which are along that axis, new axis, right? So if this is your x and y axis, the original axis or the previous axis, and then you have this x dash, which is new one, rotated axis, and you draw a perpendicular to x dash, another one perpendicular plane to y dash, right? And these stresses are your new directional stresses. and let them name as sigma x dash, tau x dash y dash, and sigma y dash y dash. This will be same, right? Objective is how to find sigma x dash and sigma y dash and tau x y dash, right? And we found a formula for that. Last class we derived it. The formula is sigma x dash is given by this formula, sigma y dash is given by this formula, sigma tau x y dash is given by this formula. There are a few points to note, right? One of the first point to note was, let us write it so that we remember it. There are a few points to note. One of them was theta angle anti-clockwise, let's say, represents theta in transformation, right? To the transformation same thing I'm going to write depends on sigma x, sigma y, tau x y, and the angle to theta, not theta, okay? There's a few things we found out in few classes. Third, what we got is sigma x plus sigma y is going to be equal to sigma x dash plus sigma y dash, right? So that's also we found out. Sigma x dash plus sigma y dash equal to sigma x plus sigma y. We also found out few things. Tau xy dash dash is 0 on planes where sigma x represents or in plane where we get sigma max and sigma mean. Right. Fifth we got is sigma max and sigma mean are 90-degree apart planes on right. Few more things I think we have written it in the last class. These are the things that we got. We got one more important thing. That is the representation of the strains together gives you almost like a circle. So if you have sigma x dash here and tau x y, x dash y dash here, then you can see that if I subtract sigma x dash from this, and then this portion is almost similar with a change in sign and cos, right? So they are almost like each other. So when you square them and add them, you get a constant which we call at radius. Right? So I can represent that as, and if you take a ratio of them, tan phi, it becomes 2xy, 2 tau xy divided by sigma x minus sigma y. This 2 and that goes there. So if I represent this angle by 2 phi, okay, phi is equal to 2 theta, then this is sigma x minus sigma y, and that is tau xy, and this is your radius r. All right, and you can write them also as equation for a circle, sigma x dash minus sigma average whole square plus tau x dash y dash whole square r square. This is an equation of a circle, and its center is given by sigma average, comma 0. So shear stress is 0, and normal stress axis is sigma average. Right. So if we start drawing it, and let's say this is our x-axis. This is wrong, I think. Right. So let's say this is my sigma axis and that's my tau xy axis. Okay. So this will represent a circle on this plane, sigma tau plane. And that the points, each point on this circle will represent one plane by itself. Okay, so there are 360 degrees, and each 360 degree will represent one plane separately. There can be many more planes based on how much resolution you want to go. How do you draw this most? Is the question that we need to answer. Okay, so I'll just stop for a minute here and ask if you have any questions. Okay. So the question that we're supposed to answer is how to draw this Mohr circle. Okay, let's start. Let's start from the very beginning, that we have been given an element, right? You have been given a material element, which is shown here, and the material element has stresses as representation, right? This is sigma x, that sigma y, and this is my tau x, right? And that can be represented in a matrix format like this. So either I can give you a matrix or I can give you this element, and I will ask you to draw the Mohr circle and probably transport the Mohr circle to find stresses on a transformed angle. But before we go to transform space, we have to make Mohr circle based on this data available. Okay. All right. So let's start it. What we do first is we need to find a coordinate axis, right? The coordinate planes are like this. Please note the coordinate planes, they have their own representation. The positive axis on the right side is the positive sigma, so positive normal stress. Okay. The downward axis is positive shear stress, and that represents a counterclockwise shear stress. Please note, we are now changing our understanding. This is a counterclockwise shear stress, and that's a clockwise shear stress, which is on the top, and that's negative. So I've written positive, negative this side, and negative, positive, positive on this side. Similarly, this side will be negative, comma negative, and this will be negative, comma positive. Okay. All right. So the shear stresses that will create, remember the shear stresses are always complementary, so they act in pairs. So if the shear stress creates a counterclockwise moment, they are drawn on the bottom side. If they create a clockwise moment, they are drawn on the top side. So let's look at it. These two shear stresses, this tau xy, what are they creating? They are creating a counterclockwise moment. So this shear stress on this plane, x plane, is a representation of a counterclockwise moment. So this will come at the bottom. But as this shear stress, it's trying to give a clockwise moment, right? From the center, if you look at, it's trying to give a clockwise moment. So this is supposed to be on the top side of the axis. Okay, clear? Right. So let's draw this x-axis. Let's point out which point. So any point on this plane, tau sigma plane, represent one of the elements, like this one plane it will represent. So this sigma xx and this tau xy, or this tau xy and this sigma xx, will represent one plane, right? Which plane is that? Which point is that? Let us look at that. Sigma xx, let's say sigma xx is positive, right? So something here, sigma xx. Okay, let's point that here. This is sigma xx, comma 0, right? That point. Now I have tau xy, so I will go like this, sigma xx, and then tau xy, which is on the negative side. So let's say this one. This is my sigma xx, tau xy. So this is my point, this guy. So I can draw it like this. Okay, and I can shade this part. Oh, instead of shading, I have rubbed it. Happens. Right? So this is the representation of that point. This is sigma x, it's tau x point. This point. All right, any doubt here? Okay. Right, so that's your sigma xx point drawn. Now let us draw this point, right? So we have drawn this one, but we know that there are two planes here, two perpendicular planes. One plane is here, the other perpendicular plane is here. So we have to draw that plane also. So how is that plane drawn? Now this is positive again, right? So it's going to be on the right side of the axis. But this guy is going to tau xy is giving a clockwise rotation, right? So it's going to be on the top side. So this point, let's say this point is so this is my sigma y, and that's my tau xy. This is going to be that point. So I've written this as sigma y, comma, s tau xy, minus tau xy. So this side is top side is minus. Now what you do is that point we have drawn in the first figure. So that point is A. So let us name these planes. This is plane A, right? And this is plane B. So that's your plane A. This is your plane A, and that is your plane B, right? Each point represents plane, remember. Okay. Now what I can do, I can draw a line between them. Okay. Remember that theta angle orientation in the material element is 2 theta angle orientation in the Morse circle, right? We have discussed that in the last class. And therefore, a 90-degree movement from this plane to that plane will represent a 180-degree shift on the Morse circle. And therefore, this is the 180-degree shift. And therefore, it's a 2 theta here. So this represents the diameter of the circle because there are two opposite planes, right? 90-degree planes, and it's 180-degree in the Morse circle. So they are diameter, right? The straight line that makes 180-degree is the diameter here, and that's the center. What do you do now? Simple. Measure the center, draw the Morse circle. You have to draw this in a graph paper, and therefore all the measurements are available to you. Okay. So now I have marked this diameter, and I have drawn the circle. The point at which it crosses the x-axis is the center of the circle, because at center the tau xi is going to be 0. Remember, center is sigma average comma 0. So that's the center. Okay. Any point on the circle is a material plane represented by 2 theta here. Any point is a material plane. Okay. All right. Now this is drawn. Okay, my Morse circle is drawn. Okay. Once the Morse circle is drawn, we need to know how to read the Morse circle. Unless we know how to read the Morse circle, we won't be able to find. If I've been asked at angle theta, what will be the stresses or strain? No, so I have to read it. So given a Morse circle, how do you read it? So this is a Morse circle that is given, let's say. Okay. Now, once this Morse circle is given, you are given the center, okay, and you are given the radius. That's how the Morse circle is drawn. Once the Morse circle is drawn, this line that we drew, the zeros, the diameter we drew, no? A and B points. So these were the points A and B. Plane A and plane B. These are the 2 points. One is here, A and B. That line is called zero line or the base line. Okay. This is called the 0 degree line, because unless we fix a 0 degree line, we won't be able to measure any other angle, right? We have to first find what is the 0 line. So your x-axis doesn't form the 0 line. Please note this. The x-axis on the Morse circle is not always the 0 line. The 0 line can be something else. So this, if I have my base element, so that's my base line in the Morse circle. Okay. Now, if I have been asked to find the stresses at an angle theta from your baseline, so this is my element which makes an angle theta with the base element, right? So that I have to go 2 theta here. So this is my baseline. I will go anti-clockwise. Here it is anti-clockwise. So I'll go anti-clockwise 2 theta. Once I go anti-clockwise 2 theta, I'll get another line. So I'll join this line, right? And extend it. This point will represent my sigma x dash, and I can see that's a minus tau x because it's on top side, right? So this is my sigma x dash, and that's my minus tau x because it's going to be clockwise. come to the opposite side, it's going to be plus sigma y. So this is plus sigma y, and this is going to be plus tau xy. So it's going to be anti-clockwise. So this is right. So that's how you draw the elemental stresses from the Mohr circle. Now from there you can come to the matrix format. So sigma xx and minus tau xy, tau x minus tau xy sigma. Is that clear? We will be asked to find what are the, to read a Mohr circle, we have to find a few details, right? So these details are given here. You have to locate the principal planes. You have to locate the principal values. You have to find the maximum shear stress. You have to determine the value of the maximum shear stress and determine the stresses at any other given plane, right? This is what you have seen right now. Any other given plane now you find, but we need to find maximum and minimum principal stresses as well as their orientation and the shear stress. Let's look at it. So this is a Mohr circle. Okay. Now this Mohr circle has been drawn with given this plane to you. So once this plane is given, this line you get 0 line. The maximum stresses, normal stresses. Remember, the principal stresses are always normal stress. Right? Maximum normal stress, as you know, will be diametrically opposite of the circle. So these are the two, maximum and minimum. So C is maximum and D is the minimal point, right? So that's my sigma max and this is my sigma mean. So I write them here, sigma max. And that's my sigma mean. Now, how is it oriented? At what angle it is oriented with this respect to this element? So this is my line. The angle I have to find from this, right? Yes, come here. So that's my angle. And that angle will be 2 theta. So I can measure this angle with a protractor. You can always do that in, you have to draw this in a graph paper. So you can always do that. Once you know this angle, which will be around maybe 30 here, in the element, it has to be divided by 2. It will be only theta p, right? So this is your sigma x max. This value will come here, sigma 1. And that value, which will be 180 degree out, making an 180 degree angle from the principal plane, which we here sigma mean. So sigma mean comes in a y, right here. So that's my sigma 2. And on these two planes, your shear stress is 0. So your tau xy is going to be 0. So the principal plane of the planes along which your shear stresses are 0. Please note the definition of principal planes are planes along which your shear stresses are 0. Okay. So the point C and point D. Point C and point D represents your principal planes. So this plane C, and this plane D. Okay. Now, how do you find maximum shear stress? Of course, you know how to find it. This is going to be the tip point here and bottom point here, right? And they are just radius of the circle. So you can just use the formula of the radius of the circle, which is, right? How to find the formula of the radius of the circle. Remember or forgot? So it will be sigma xx minus sigma average whole square, right? Plus tau x square whole square. That will give you. So this value whole square plus this value whole square will give you the value whole square here, right? And that's the radius. Or what you can do is principal plane you have, right? Principal points you have, this principal point minus this principal point divided by 2. Right? Maximum principal minus minimum principal divided by 2. That will also be your sigma xx minus sigma y by 2. That will give you R. So this is what. All right. Clear? And how do you find the plane at which it is acting? You again get the angle between your 0 baseline. So this is always, we call it 0 line, okay? Or baseline. It's written here, right? So this is sigma 1, this is sigma 2. So you know this angle 2 theta, so it will orient by theta angle in the material plane. So you can draw the material plane theta angle. And then you can always try, right? So shear stress on this is going to be negative, on this is going to be positive. So this is your negative shear stress. And you can find the normal stress at that point. The normal stress is going to be always the average shear stress, right? So this is your average shear stress. Yes, stress, and other things. Okay? All right. Good. Some interesting points are given here, which you have to go through, which I've written already, I've told already. For principal planes, sigma max 1, sigma max 2, what you have to do, all these details are given. Please go to the principal planes are 90-degree apart, which I said on the material point, okay, material point element. But 180-degree in the Mohr circle. The point in a Mohr circle represent principal planes are at the x-axis, where tau is always 0. The principal planes makes 2 theta p angle with the baseline, right? Baseline is 0-degree line of the Mohr circle. Maximum shear stress makes an angle 2 theta p plus 90-degree. Why? If you go here, you can see this is your 2 theta p, right? Plane stress angle plus 90-degree. Okay. So 2 theta p plus 90-degree. So if you know theta p, you can find theta phi s. Okay. And tau max is given by sigma 1 minus sigma 2 by 2. Okay. Maximum shear stress plane is 45-degree away from the principal plane. This is very important. 45-degree angle in the material point coordinate. Let's do a few problems. Before that, let me stop. I've been given a problem here where this is the element that is given. Element has 50 MPa as its sigma x, 10 MPa compressive as sigma y. We solved it in the last class also, and 40 MPa as it tau xy. Right. So in matrix, I can write it as this one. I take this matrix and bring it below. Yes, very nice. So in matrix, I can write this one. All right. Now, how do I draw the Mohr circle? I've been asked to find principal planes, principal stresses, and maximum shear stress and corresponding normal stress. Very easy to draw a Mohr circle and do it. You can do it with analytical formulas also. There is no problem with that. But learning Mohr circle is much better because that's more easy to do. What I have to do is I have to take axis, right? I have to take 2 axes. One I will take along. Let's make it a black color. Yes. Yeah. This is one axis. That is one axis. Okay. This is my positive sigma, and that is my positive tau. Let's look at the first plane here. The first plane is 50, 40, right? This is my first plane. First point should be A point. So A point, I'm writing it as A point, point A. Where do I write A point? Okay. A represents 50, 40, right? Now let's look at whether it's positive 40 or negative 40. So this shear stress is like this, and it's going to go anti-clockwise. So positive 40. So that's positive. Now let's look at B plane, B point, another point, which is 90-degree to A. So this is the plane. B is going to be 10 minus 10 because it's comprehensive, right? Minus 10, comma, clockwise, right? So minus 40. Okay. Minus 10 since compressive. Minus 40 since clockwise movement. Okay, very nice. We've done it. So let's look at point A. How do I represent point A? So let's say that this is my 50 here. So let's go by 10, 10, 20, 30, 40, and 50. Very nice. So that's going to be 50. And then I have to go 40 again, right? So let's say 10, 20, 30, 40. So this and this, right? So it will be somewhere here. This is my plane A, which is given by 50, 40. Now let's look at the B point, which is going to be 10 here. So that's my 10, minus 10 and minus 40. So 10, 20, 30, 40. So somewhere here. All right, somewhere there. So that's my, okay, that should be, that should not be black, that should be blue according to my color combinations. So that's my blue. And that can be written as minus 10, minus 40. If I make a mistake, please let me know. And then what I'll do, my next job is to join these two lines, right? Very nice. Very good. So that's my zero baseline is drawn. So this is my 0-degree line. Drawn. What I have to do, I have to find sigma average. So this is my point of sigma average, right? This is my sigma average, 0, center.
Sir?
Yes.
Sir, in matrix, they give plus 40, right? Plus 40 minus.
Yeah, matrix, both I'll put plus 40 because matrix representation is different and this representation is different. Most circle representation is different. Matrix representation goes by this side. I've already made these signs, right?
Got it, sir. Got
Matrix
it.
representation based on this sign. So this is my positive matrix representation. Okay. Clear. And it has to be always symmetric. You cannot put minus here and plus there. So for a matrix representation, this representation is positive shear stress. Whereas in Morse circle, it depends on a different visualization. So we look into the moments, how they are creating. Okay, so this is my diameter and therefore I know the radius, right? Now I can do is I can draw a circle here. Very easy to draw a circle. Let us draw a circle. I don't know, whether I can draw an easy circle from this. Ah, very nice, fantastic. Very good, man. Technology has changed. And it has changed how how people can do things easily. So that's my motorcycle, perfect motorcycle, Probably first time I'm drawing a perfect motorcycle live. Okay, so that's my motorcycle. And the point where it crosses, so let's extend this line a little bit here. All right, the point where it crosses this is my principal stress, right? So let us put it with the green color. Okay, that's my sigma 1 and that's my 2. So if I have to draw sigma y sigma 2 plane, how do I draw? So I have to find this angle also. Let's say this angle is 2 theta p. You can measure it, right? You have a protector, you can measure it. I don't have that here. You can measure it. So I can draw that plane. The plane is going to look like this. Remember, it has gone anti-clockwise, so it has to go anti-clockwise again. So that was my initial plane, which was drawn in black. Anti-clockwise had to go, so anti-clockwise theta p will be in green. This is theta p, remember, not 2 theta p, this is theta p, okay? And similarly this way. So the stresses are going to be sigma 1, this is also sigma 1. And then I'll go 90 to it, which represent 180 here, right? So this is my sigma 2, 90 to it. And that's going to be my sigma 2. And that is compressive. That's not tensile. Please note, that is compressive. This is negative, right? This is negative axis of sigma. So it's going to be compressive here. What about shear stress? There is no shear stress acting on it. Because these are principal plates, no shear stress. So that's my elemental diagram for this point here. Okay. All right, what would be the elemental diagram for this point? Can anyone tell me what would be the elemental diagram for this point?
Hello,
Yeah.
sir.
Yes.
Sir,
Yes.
you have drawn compression for sigma 2 and return sigma 2. It's already negative, so
No.
magnitude and direction.
Yeah, I have written sigma 2 here, not minus sigma 2. So in element, I have to represent it, right? Sigma 2 is the value there. For example, if you see this diagram I have drawn here, the diagram here in the problem that is given, 10 MPa is the magnitude given, right? And the direction is given by the compression. So that's the magnitude here. Okay.
So that should be mod of sigma 2, right?
Oh, well, if you insist, yes, I can write mod, but this is how you represent it in engineering. You don't write mod, you write only the value and give the direction.
Okay.
Yeah, if you insist, I can give a mod, but that's not how you write in any of the strength of materials book or engineering. So you take it, you learn it from here. It said that you remember that they have given a direction, so that represents sigma 2 represents only the modulus of it. Now, what I was telling is, yeah, the material element drawn here. How do you draw the material element? So let's draw the material element. Again, let's take help of a green. So the material element is going to be 180-degree opposite to that, right? So it's probably going to be, let's see. Okay. And now it's theta. This is not theta p. This angle is 180 plus 2 theta p divided by 2. Okay, so it has completely gone on the other side, right? So that will be 90 plus theta p. Okay. Okay, let's that is my it's going to be 90 plus theta. So it's going to be that's my black axis. And that's my green axis. Right? And yeah, this is my black axis again. That's again my green axis. So this is the angle. Okay. This is the angle, and that angle is given by 180-degree plus 2 theta p divided by 2. Okay. So now the stress, if I draw the stresses, this is going to be your compressive stress, right? So that's going to be your compressive stress 2. So this is also going to be your compressive stress 2. Again, please don't tell me I have to draw mod. Clear? Same diagram. Now let's look at shear stress. I have drawn all those things here. You can see it. The things I have explained is drawn here also, and the values also I have found. The values, if you have a graph paper, it's easy to find the values. So if I represent each one of them as a 10, if you don't know how we represented it, let's say this was the point, right? So 1, 2, 3, 4, 5, yeah, 50. So each one of them was 10. So now I can find this point, right? Sigma is 1, 2, 3, 4, 5, 6, 7. So around like 71. Okay, actual value is 70. All right. And then we have sigma mean. Sigma mean is also you can find 1, 2, and 3. So it comes out to 30. So 30 plus 70 should be 100. Here also, yeah, 30 plus 70 should be 100 by 2 is 50. Okay, and then shear stress. How do you find shear stress? So this is the maximum shear stress, right? Okay, that's your maximum stress, and the value is going to be given by 10, 20, 30, 40, 50. around 51. Because this is just a little bit up here. So from graph, I've got 51. Maybe it will be 50 or something. It can be 50. Okay. So this is the plane D. Okay, that's D point. This is plane D. That's E point. And the E point we have drawn. And now we have to draw shear stress, right? So this is the shear stress plane. Let's say this is my plane. No, sorry, this is my plane shear stress plane. And that will be 45 degree plus theta P. This angle is 45 degree plus theta P. We have just explained that. And let's see here at this point what happens. At that point, you have your shear stress to be sigma average, which is 10, 20 around, right? So you can calculate, right? 50 plus minus 10 is 40 divided by 22 is 20. So that's going to be your 20 sigma dash the sigma average, which is going to be equal to 20. And your tau is, we have found around 51, so it is around 51. Around 51, okay, right? And you can see that it's on the positive side of the axis, so it's going to be on this one, anti-clockwise. Sorry, it's on the positive side of the axis, so it's going to be, sorry, negative side of the tau axis. Sorry, it's on the negative side of the tau axis, so it's going to be clockwise like this, and then you can draw the other ones, right? Sigma y, on the opposite side, you come here. That's also sigma is positive, so it's going to be positive again here. So that's how you draw sigma y, sorry, positive here. And that value is also same, going to be 20. Now we check sigma 1 plus sigma 2 is 71 plus minus 30 equal to around 40. Let's say around 40. Sigma 1 plus sigma 2. 41. Let me write it 41. Why not? It can be a little bit erroneous when we're doing this. So around 20.5. All right, which is almost near to your what you have been given as sigma. Okay, so do these problems by yourself that are given here. I'll stop here. I have given how. So can you quickly tell what will be the diagram for this? 4 seconds. Quickly, any one of them. Any one of them. Quickly. So there is no shear stress, right? This element has no shear stress. And since it doesn't have any shear stress, these are the principal stresses itself. So they will work like this point, and then 0 degree line is the x-axis itself here. All right. What about shear stress? There is no normal stresses here, right? So you can draw it. Normal stresses are 0. So 1 point is here, 1 point is here. So it's a circle like this. Okay, with a center point to be origin itself. And you can then find the normal stresses. So draw these things yourself. I've explained them also. Okay. All right, I'll stop here and probably will carry on from here in the next class.